Good afternoon, folks. So now I'll be talking in this session about how MySQL HeatWave can be used for processing queries on data which is in the object store, which we also refer to as MySQL HeatWave Lakehouse. Hopefully by now you have understood the key message of MySQL HeatWave, which is it's a fully managed service from Oracle, and it's a single database service which offers efficient support for transaction processing, analytics, and machine learning. It's 100% compatible with MySQL syntax, so all existing tools and applications work as is with MySQL HeatWave. The performance of MySQL HeatWave is better than specialized databases. So MySQL HeatWave is a general purpose database for multiple workloads, but if you compare the performance of MySQL HeatWave with a specialized database like Redshift or Snowflake, which has been designed only for analytics, even then, this general purpose MySQL HeatWave database comes across as much faster and much less expensive. So for instance, it's about 30 times better price performance compared to Snowflake. But there is a huge growth of data which is outside the databases. So if you look at the amount of data which is outside the database in a file system or an object store, that's much more than it's in a database. And what we have been observing is that more and more it's a case that our customers have a combination of some data, perhaps transactional data in a database like MySQL, but also like a bunch of data like log files, files from sensors and such in the object store, and they want the capability to be able to query that. In order to provide query processing on data which is in the object store in files, we have offered this capability of which we call MySQL HeatWave Lakehouse. It is the same MySQL HeatWave service, same service, but it allows users to connect to an object store and do query processing on top of that data. One of the very marquee points to note is that even when we are allowing query processing of data in the object store, which could be in a variety of file formats, CSV, Parquet, Avro, the syntax which customers need to use is standard MySQL. So what that means is that customers can take their existing applications, and if the data is in InnoDB or MySQL, that application works. But if the data is in object store, those applications would work with slight changes to kind of point the source files to be the object store as opposed to InnoDB, right? So existing tools and applications which are compliant with MySQL will work with very minimal changes, and the only change is that you're pointing the source of data to be the object store. And this is an example over here where we have a CSV file, the sensor file, which is in the object store, and you have the sales table, which is in the InnoDB database or InnoDB storage, and you can run queries which cut across the transactional table, which is the sales table, and combine it with the sensor file. What is very interesting is the performance of HeatWave on object store. Now, typically what happens is when the data is in the database, we get a lot of interesting statistics from the data. Like for instance, what is the cardinality, right? What is the data distribution? And when the query optimizer optimizes or generates an execution plan on this data, it has the statistics, good statistics, so it can come up with good plans. But when the data is in the object store, you don't have these kind of statistics. So what is very interesting is that HeatWave is able to so efficiently process data which is in the object store. So like 400 terabytes of TPCH data, an average query takes about 42 seconds with HeatWave. The question is, how do we do that? Well, let's look at what the competition does. So when you look at this comparison of 42 seconds with Snowflake, HeatWave is 17 times faster on an average for query processing compared to Snowflake. HeatWave can load data about 2.7 times faster than Snowflake, and it costs 30% less. In addition, HeatWave is the general purpose database, so it can do transaction processing plus machine learning inside the database. So HeatWave is giving you these additional capabilities which Snowflake does not, yet for the things which Snowflake does, HeatWave is faster to query, it's faster to load, and it is less expensive. Because typically if you think, right, there are some databases which take more time during ingestion and then they are fast for queries. Or some databases are very fast to ingest and they take a little longer time to run queries. This is very interesting about HeatWave, that HeatWave is the most efficient, is the fastest database, and we did a comparison with Redshift, Snowflake, Google BigQuery, and Databricks. It's the fastest to load, and it is also the fastest to query. Now, one important point which I want to highlight is that although we have this HeatWave cluster attached to InnoDB, where you can have transactional data, and you can use the same HeatWave cluster to process queries in the object store, data which is in the object store continues to stay in the object store. We do not move the data from the object store to InnoDB. The only thing which is done at the DDL time is we create some metadata which describes the mapping of the file in the object store to some corresponding table in the MySQL database, right? So we do not move the data out of the object store. The data remains as is. Now the question is, why or how is the processing performance of HeatWave so much better than what other vendors do? Well, in the case of query processing, it's really the case that HeatWave has been designed for scale-out query processing. What we do is when we read the data, we partition the data into very fine chunks, and these chunks typically fit in the cache of the underlying machine. And then we have come up with new algorithms so that we can process these partitions at near memory bandwidth, or in some cases near network bandwidth. So the data is loaded into the memory based on the queries, the data fits in the cache, and then we process these partitions really fast. That's the reason the query processing of HeatWave is so efficient. Similarly for loading, we now have a scale-out mechanism to load data. When the data is read from the object store, there is some amount of variation depending upon, say, the data type, or depending upon which exact chunk you're reading from the object store, where there could be some difference in the latency of processing the data, because we're taking the CSV representation, and when we're reading into the memory of HeatWave, we're converting it into a hybrid columnar representation. So there is some latency which would vary based on the object, on the data type and such. Based on the super chunking technique we have, we are able to mitigate the impact of stragglers. So suppose there is a slight variation in latency because we are getting it from a different disk and such. The super chunking ensures that the cluster is being fully utilized all the time while loading the data. This is the reason load performance of HeatWave is so much better than what we see with other database services. The net result is the scale-out performance, right? The query performance of HeatWave scales nearly linearly, right? And these are end-to-end queries. So I'm not showing the scalability for primitives. This is the end-to-end query which is scaling so well. Now, one thing which is very important innovation in HeatWave is Autopilot, which is the machine learning based automation. Autopilot has two benefits. One, it helps with the query performance. And secondly, it helps with management. And I'm going to give you examples of both. So take the case of the schema inference. When we read the data from the object store, whether it's a CSV format or Parquet format, the user doesn't need to define the mapping of the CSV file to data structures or schema objects inside the database. This is automatically done by Autopilot, and I'm going to show you a demo at the end of the session. Now, an example of performance is data placement or auto partitioning. When we read the data from the object store and we populate it in the memory, the way the data is laid out is such that it minimizes data movement during query processing across the nodes. And that's done based on the queries. So if we know what the queries are, based on the queries, we partition the data so that it minimizes data movement. Similarly, we have this feature of auto query plan improvement. Here, the optimizer learns from the statistics of the previous queries. For instance, what was the size of the intermediate results, or what was the cardinality of an operator from the previous queries. And based on the results or the intermediate results of the previous queries, the system learns from it and does a better job in terms of creating better execution plans for the subsequent queries. So the system keeps getting better over time. And this is something which plays out really well for data in the object store, because there you have much less information than, in terms of statistics than you would have for tables inside the database. Now, one benefit of this, one characteristics of this is that the performance of HeatWave for queries is identical whether the source of data is inside the database, meaning tables, or whether the data is coming from the object store. Typically what happens is when the data is in the object store, systems which are able to process it, they take some hit in terms of the query performance. As you can see over here, I'm showing two workload sizes, 10 terabytes and 30 terabytes. The number of nodes required are the same. the query performance is identical. This is a very, very marquee feature, and the reason we are able to accomplish this is because of autopilot, because it learns from the previous queries and very quickly it's able to get very accurate statistics for data which is in the object store. Now, if you do a comparison of HeatWave with Redshift, Snowflake, and Databricks, so this is a 400 terabyte TPCH workload, right? And this is the largest benchmark we have seen. We have not seen anyone run 400 terabyte TPCH. CSV format, data is in the object store. The first row shows you the cost difference. HeatWave is about 30% less expensive. The second row shows the load time. How long does it take to load this 400 terabytes of data? In the case of Snowflake, it takes 11 hours. In the case of HeatWave, it takes 4 hours. For Redshift, for Databricks, it's about 30 hours, right? Big difference between 30 hours and 4 hours. And then look at the average query time. With HeatWave, it takes 42 seconds. With Snowflake, it takes 700 seconds, 17 times slower. And with Redshift and Databricks, it takes about 250 seconds, which is about 6 times slower. So what you find over here is across the board, across all the three other database services which are specialized in doing query processing on object store, HeatWave is faster to load, faster to query, and less expensive. And HeatWave is a general purpose database. It does transaction processing, it does machine learning, all these other things as well. But even for the things which these other databases are good at, HeatWave beats them in all the metrics which matter. Now, so I was showing you the numbers for the CSV format, but now if you look at some of the other popular file formats like Parquet, well, we are able to ingest a wide variety of file formats. We can ingest Parquet, we can process Avro, we can process export from Aurora, export from Redshift. And one of the interesting characteristics of some of these formats like Parquet is that they lend themselves very close or very similar to HeatWave's hybrid in-memory columnar format. So Parquet is pretty similar to the hybrid columnar format, and the result of this is that it doesn't take us much longer to either load or to query the data. So the first two rows show the load times between CSV and Parquet. Both of them is about 2 hours to load 10 terabytes on 12 nodes. Once the data is in memory, it doesn't matter what the source format was. The query time will always be the same. Right? Whether the source is CSV, Parquet, Aurora export, Redshift export, doesn't matter. The load time could vary, but we see that for CSV and Parquet it's the same. In the case of Aurora backup, it takes longer, and the reason is because the Aurora backup is not optimized in terms of the Parquet layout. And if you were to ingest using Redshift, it takes much longer than it does with HeatWave. So we are efficiently able to transform the data. Now, this is an example of what I was talking about of using HeatWave or MySQL Autopilot. There's one aspect of Autopilot which helps improve query performance, but there's another aspect which is in terms of ease of use, which offers ease of use. So when you have data in the object store in a file format like CSV, in most of the systems, the user or the DBA is expected to provide the mapping between the file and what would be the corresponding schema in the database. With MySQL HeatWave, this is done automatically with Autopilot. So the system determines what is the size of the file, it determines how many columns there are, it determines the appropriate data type, it determines the precision and such. So this is something which makes it very easy for customers to be able to bring in new kinds of files or new files and not have any latency or downtime before they can be queried. In the beta engagements we had some customers, this came out as one of the key highlights or advantages customers identified about HeatWave, the ability to be able to process a variety of files without requiring a human intervention to define the mapping. Another such example of Autopilot ease of use is auto-provisioning. The system is able to determine what is the size of the file in the object store, how much of memory it will take, how much of time it will take to load. Right? So when you're doing some processing, you have a very good idea how long it's going to take. And this is done not by sampling the entire file. We sample about 0.01% of the file, and we're able to do this. Now, one of the points to highlight is that when the data is in the object store, the opportunity is that we can get this data in the object store from a wide variety of sources. It can be from files, it can be from other databases. So I'm going to show a demo where I'll show you an export from an Aurora. You can have an export from Redshift. You can export from Oracle database, from Postgres, right? At the end of the day, as long as the file is in one of these formats and it's in the object store, it can be processed by MySQL HeatWave. So to summarize, what we have with HeatWave, we can now process data which is inside the MySQL database or in the object store in a variety of file formats. Processing of data, whether it's inside the database or in the object store, has comparable performance. Even when you're querying data in the object store in variety file formats, the API which users use is 100% compatible with MySQL syntax. So the endpoint for the users is still MySQL. They use the MySQL node to run the application. Although all the processing is happening on the HeatWave side, but MySQL node is still the endpoint. HeatWave offers the best performance and the best price performance both for querying data as well as loading data. Autopilot, particularly in the context of the object store, significantly improves the manageability and performance of processing data. And this capability is currently available in beta in OCI, and very soon we will be rolling it out as GA. So with this, I'm going to show a demo here. Okay, so what I'm going to show in this demo is processing 250 terabytes of data with HeatWave. Now, some of these things like loading the data takes a couple of hours, and that's why what you're going to see over here is a recording. So the user comes in to the OCI console, and from the OCI console, the user can pick the database, and in this case, we'll choose a MySQL HeatWave instance. So this is the capability of Lakehouse, which is enabled. So the queue is, if this HeatWave Lakehouse is enabled, this is a queue to the user or to the application that this database can now process data in from the object store. So let's look at what do we have in the object store. So for this demo, we have 250 terabytes of TPCH data. TPCH has 8 files. So 7 of the 8 files, we have them in the object store, right? And there are these different files in different file formats. Line item is the largest table. It is about 200 terabytes in size. And then we have some files which are in Parquet format, some files which are Aurora export. Now the first step is I'm going to invoke the Autopilot. And what Autopilot does is it looks at the object store, does a very small sampling, about 0.01% of the rows, and is able to glean some useful information. This is the output from Autopilot, and Autopilot is indicating that the size of this file, line item, is 195 terabytes, and it has 1.5 trillion rows, right? So this is an estimation which Autopilot is doing. Furthermore, Autopilot is able to predict that it's going to take about 2 hours, 2.16 hours, to load this 195 terabytes of data from the object store to the memory, and the memory consumed will be 8.8 terabytes. And it requires a cluster of 211 nodes. This is all done by a machine learning model in Autopilot. Next, when we look at the schema, this is something which is automatically generated by Autopilot. It has identified how many columns there are. It has defined what the corresponding data type should be and what the precision, for instance, in the case of number should be. Now we're going to run this standard alter command, and this alter command is now going to load data from the object store to the memory. And you saw it took just about 2 hours. This is another example of the Aurora export. This is a file which was exported from Aurora. Very similarly, you can get the information from Autopilot. It is all integrated with VS Code. So MySQL HeatWave is now integrated with the VS Code extension which we have. We can run the alter table command to now load this table Aurora export into the memory. Now finally what I'm going to show is that we have a table which is in the MySQL database, right? So we have 7 files in the object store. One of them is in InnoDB, and we're going to load this table into memory, right? So those are 3 tables I showed, and the rest of the 5 tables in the background we have loaded. So in total, we have 8 tables which have been loaded into HeatWave, and now we're going to issue this query. And this query is a 7-way join. So we're going to run the 7-way join query, 250 terabytes of data on about 350 node cluster. Now think about it. when you're doing a join, right, the complexity of the join many of the times is nonlinear. We have taken all of these tables and we are doing a multi-way join, and this is something which is going to scale out with the size of the cluster. So one of the interesting things is, regardless of the size of the data, the performance does not change very much. So you can see over here, we were able to process the 7-way join onto 50 terabytes of data in 41 seconds. Now what we're going to do is, MySQL is a transactional store. We're going to update the table which we loaded in InnoDB. So I'm going to, over here, update one of the rows over here to show updated. And we will commit this change. And now we're going to rerun the same query. Now HeatWave also offers real-time analytics. What that means is any change which has been made to the transactional store will be updated in real time. So we run the query again, and you can see the results were updated. Right? So what I've just shown you is the capability where MySQL HeatWave can process data both from the object store as well as from InnoDB. The processing is done in a scale-out manner. So I was showing you that in the earlier benchmarks that about 400 terabytes of data takes 42 seconds on an average to query. This is 250 terabytes of data, smaller cluster takes about the same time. This is what we mean by scale-out query processing. As the size of the data grows, the system scales accordingly and is able to provide you with good performance. And with this, I'll conclude my presentation. Happy to take any questions.